Hello, welcome to this video about Brian Kernighan's big idea. My name is Dalton and I'm an embedded C programmer. Let's get into it. Before providing the algorithm, I'm going to provide a naive solution, an inefficient way to do this that one might try if they don't know this trick. My solution is going to loop while n is not equal to 0. And as we continue through this loop, I'm going to divide n by 2. Yes, this is the same thing as shifting by 1, but this video is going to be short. The next thing I'm going to do is I'm going to check if n is odd. So we do n modulus 2, which gives us the remainder of a division by 2, and if it's not equal to 0, then n must be odd. Okay. And then once I know that the number is odd, I know that the first bit is set, and that's because in a binary number, the first bit represents the ones place. If the first bit is set, that means I have a 1. So I'll keep track of how many ones that I encounter in the ones place. And then the purpose of dividing by 2, which is it really should be a shift to the right by 1. We have to shift the binary number to the right, and that moves the 2-bit into the spot of the 1-bit. And we continue doing this until n is 0. And then we escape our loop, and we can return our count. Now, please don't complain, compiler. Okay, we run that. As you can see, the binary representation of this number is 146, has 3 set bits, and the naive solution correctly detects that there are 3 bits set in this number. But what if there was a better way to do this? A way to do this in less time. This is where Brian Kernighan's algorithm comes into play. The algorithm itself is very simple, so I will just provide the implementation. So we take the number and we bitwise AND it with the number minus 1. And this will extract the first set bit in the number. I'll put it in the comment above because this isn't exactly how we're going to use it. Say, doing this group of operation extracts first. It extracts and clears the first bit that is set from the number n. Let's show an example of this because it doesn't make sense intuitively. Let's say we have a binary number 10100. This number is, so we have the 4th place set, and we have the 16th place set. So this is 20. We're going to do Brian Kernighan's operations on this number and see what it does. If it does what I say it does, it will extract and clear the first bit that is set from the number. So we would expect the result of this operation to be 16. So let's do it. First, we have to do 20 minus 1, which we know that this is 19. The binary representation of 19 will be, so we'll take 16, and then we need 3. So this is 16, the 16th bit is set, plus the 2-bit plus the 1-bit. Okay, and then there's a pattern that emerges from this subtraction. Subtracting 1 from any number n will always clear the first set bit, which was in this spot for this number 20, and set all the previous bits before it. So this was step 1. Subtract 1 from the number. Now step 2 is we bitwise AND the original number from the number minus 1. So what this will look like is we will have the original number, which was 20, and the original number minus 1, which is 19. And we bitwise AND these together. Bitwise AND means that only numbers that are both 1, or bits in each bit in both of the numbers has to be 1. So we will say 1 for 1 and 1, 0, 0 for 1 and 0, 1 and 0 is 0, same thing here. And now this yields us the number 16. This is the number we were expecting. And this number is the 20, but with the fourth bit unset, and that was the first set bit. This is the genius insight behind this algorithm, because what this means is we can apply these operations to the number over and over again until the number is 0. And then however many times we're able to apply this operation before it's 0, that is how many bits are set. So what we will do is we will say while n is not equal to 0, and we'll just apply this operation. We'll say n is equal to n bitwise n with n minus 1. And then we need to keep track of how many times we do this. So we'll say count plus plus. We'll return our count. Don't forget the semicolon. So with that, we'll do a quick compile, run it. As you can see, using Brian's solution, the number 146 has 3 bits set. That's really all there is to it. It's a clever trick that reduces the amount of operations very slightly. What if I want to know if a number is a power of 2? A binary number is a power of 2 if it only has one, I'll say one ones bit set. So from this fact, we can use Brian's algorithm to test if a number is a power of 2. What should happen is after we apply Brian's algorithm, the number will be 0 because we've extracted the first set bit. So there should be no more set bits, it'll be 0. But if the number has more than one ones bit set, then this number will be non-zero, and thus it's not a power of 2. And there's also a base case. N cannot be 0 because 0 would be undefined. A power of 2 is written as 2 to the x. So 2 to the x equals 0, that is undefined, a short base case. Okay, but as you can see, Brian's algorithm is very neat because you can extract out the first set bit and you can use it to count how many set bits there are and tell if a number is a power of 2 in a very quick and efficient way. Well, with that, thank you for listening. Stay C-pilled.